All right, it's Mr. Wagner here. Like I had mentioned, we got to do a virtual lesson here. And with our virtual lesson, I'm sorry I can't be there in person. I think we left off in class right around this slide here, light and color. I think it was actually the one right after this. But let's review this here for a second. When we were talking about light and color, we said that if you were to add all the wavelengths of color together, red, orange, yellow, green, blue, indigo, violet, you put them all together, they equal white, right? So from the sun right here, where my mouse pointer is, you can see that there would be white light, which actually contains all the colors, hitting something like a red apple, and then the red apple is absorbing orange, yellow, green, blue, indigo, and violet, but it is not absorbing red. So the color and the difference, the color, if different objects, is determined by which wavelength of light that object reflects and absorbs. It should say the color of different objects. My bad. We need to fix that. All right. Next, like red objects absorb all the colors except for red, and then next, yellow objects absorb all the colors except for the color yellow. So let me ask you about this. What do white objects do? Suppose these bananas were white. If these bananas were white, what would they reflect? Would they reflect? They would reflect all the colors together. So if these bananas were white, they would reflect the blue, the green, the yellow, the orange, the red, the purple. All those things would be reflected together. When you mix all the colors together, it makes white light. In the past, when I did these YouTube videos, I was able to put a link somewhere on the screen, and you click the link in order to watch a video. I'm going to put it down in the description down below. I highly suggest you watch this video, TED Ed, How Color Works. I'm going to have a link to that down in the description. Please watch that. It's like 4 or 5 minutes, but it really describes how light and color works. Okay, so I already asked you this. What do white objects do? I think we already talked just a tiny bit about this slide as well, where we said how light is reflected and absorbed by these two cars, or how is light reflected and absorbed. I told you the story about my white Corvette, my black Corvette. Of course, completely false. And then I asked students, which one would you rather get in on a very hot day? And they said the white Corvette. And I asked why. And they said the white Corvette reflects all the light. And it does. It reflects all the wavelengths of light. But what about the black Corvette? It reflects none of the wavelengths of light. Therefore, the black Corvette is going to be a lot hotter at the end of the day. So like I had mentioned, white light reflects all the colors of the spectrum, and black absorbs all the colors of the spectrum. The black car will have absorbed significantly more energy throughout the day, and therefore the black car will be hotter. I got some pictures I want to show you up here. Take a look at this. So we've got this picture. We've got all the different colors of white light. Remember, white light contains all the colors. All these colors are hitting a black surface, a black medium, and the medium is absorbing all the energy from that. This is supposed to be white. For some reason, when I copied and pasted, it turned out transparent, but it's supposed to be white. And white light hits a white surface, and it's going to reflect all those different wavelengths. Remember, red has got the longest wavelength, and then it goes down to violet, which is a shorter wavelength. And then just beyond violet, you have ultraviolet, and then X-rays, and then gamma rays. Let's continue. Let me move out of the way for just a second. So light and color. There's three primary colors of light. There is red, there's blue, and there's green. Now, depending on what kind of computer screen you have, if you look super closely, I'm talking really, really close, and it's probably got to be an older computer screen, you're going to see something a little bit like this here. Even a lot of TVs, if you look close enough, it's got those three primary colors, the red, the blue, and the green. And whenever TVs need to display white light, these little LED screens with the red, the blue, and the green, they project at full blast. And then to our eyes, that appears white. It's even the same thing on a phone. It's really hard to see because our phone, the resolution is so good, but we've got these little tiny pixels in here, and they're actually like projecting the three primary colors, which our eyes observe as white. So when the three primary colors are mixed, they create white light. Let me move out of the way here a little bit. Like televisions and computer monitors, they combine the three primary colors in varying amounts to achieve any color. A fun little demonstration that would have been fun to do in class, but we'll do it right here, is this color wheel. We can see that we've got the different colors of the electromagnetic spectrum, and this would probably work if it only had the three primary colors of red, blue, and green. That's not a test question, the three primary colors. But look down here, you combine those things, you're going to get white light. But if I take all these colors, put it on this color wheel, and I were to spin this wheel, it's going to blend all the colors together. You tell me what you see once they're all blended together. Sometimes this doesn't work, but let's give it a try. What color do you see? You should see white. If you're looking at this, you should see white. And now there's all the colors again. See, you're blending all the colors together and you're getting white. That's just a fun little demonstration to do in front of your class. You can actually build something like that using like string and a cat's cradle. You can do that in your classroom. It's a fun little demonstration on color. Let's go on to mirrors really quick. There's three major kinds of mirrors. The first kind of mirror is called a plane mirror. And when I say plane, I'm not talking about plain like yogurt. I mean P-L-A-N-E. A P-L-A-N-E is a flat surface. So a plane mirror is a flat surface that produces a virtual and an upright image. I'm not going to ask you test questions on what is a virtual versus a non-virtual image. There's some science behind that, but we're not going to do that. But if you're looking at this mouse looking in the mirror or this lady looking in the mirror here, both of those are through plane mirrors. They're looking at plane mirrors, and you're looking at a virtual image, which is upright and of the same size. And I just, isn't there Justin Timberlake song? All right. Let's go on to the next slide. Mirrors. So we just talked about what a plane mirror is. One of the three types of mirrors is a concave mirror. A concave mirror is a mirror with a surface that curves inward, like the inside of a bowl or the inside of a spoon. That's a concave mirror. It reflects light to form a focal point. So even though this satellite dish right here is technically not a mirror, it does reflect wavelengths of light. And if it's reflecting wavelengths of light, it's angled such that all the wavelengths bounce off of this dish right to the focal point, which is right here. It's the actual antenna that collects all the information that the satellite that's hitting the satellite dish. Here's kind of a diagram of what's happening in a concave mirror. You can see these rays of light are hitting the concave mirror and they're bouncing off and they're coming to a focal point right around there. If we're looking at a concave mirror, it doesn't always produce a virtual image. And like I said, well, that's not terribly important right now. But if you're beyond the focal point, the image is upside down. If you're within the focal point, the image would be right side up. I happen to have a concave mirror, like everyone does. And if you look at this concave mirror, I don't know, it's going to be kind of hard to do, but everything that you see here in this concave mirror is upside down. That's because everything is beyond the focal point. But if you were to look at your eye, which is hard to do because now it's a camera, but once you get it within the focal point, everything will flip right side up again. It's just got to be within the focal point. So beyond the focal point, everything goes upside down. And that is a concave mirror. It focuses all the light, just like what we see here. It focuses all the light into one point, and then beyond the focal point, the rays, like the rays that would have hit the bottom of the mirror, go up, and the rays that hit the top of the mirror would go down. I do ask a test question, pretty sure I do ask a test question about light hitting either a concave or a convex mirror. So take a look here. The candle is beyond the focal point, which is why it's upside down. And here the candle is within the focal point, which is why it's right side up. All right, let's keep moving. Next. So here's the next kind of mirror. It's a convex mirror. Convex mirror, it's bowed outwards. I don't know if you've ever looked at one of those Christmas ornament bulbs, and you looked at it really closely and it's rounded and it kind of stretches everything. That would be a good example of a convex mirror. The convex mirror, you can see it actually makes the images look a little bit smaller. So on the other side, this mirror looks smaller. But it does increase your field of view. Take a look at our ray diagram here. The rays are hitting this convex mirror, and then they're bouncing out. All this stuff back here is imaginary, so ignore that right here. This is the real light hitting and then spreading out. I happen to have a convex mirror like everyone does, and it's kind of hard because you're looking at a camera. It would be really nice if you were looking at something else other than a camera. If you have a metal spoon in your dorm room, that might be a good idea to look at. But notice everything stays right side up. It doesn't flip upside down, but it actually gets smaller as you're further away from the mirror. So the further away you are from the mirror, the smaller it gets. Okay. And I also need to tell you, it reflects light waves outward, and it produces a virtual image that's smaller. Remember, the virtual image is right side up, but I'm not going to ask you what is a virtual and a non-virtual image. You don't need to know that. There is a video that goes along with this. I highly recommend that, and you might want to pause for a second so you can click on it down in the description. All right, let's go. Lenses. So there's two types of lenses. I suppose you could say there's a plane lens, which is just like a flat sheet of glass, and light doesn't do anything fun in a plane lens. One kind of lens is a concave lens. Concave lenses are thinner in the center, and they produce only virtual images. Sometimes they're used in eyeglasses. Look at this little ray diagram right here. The beams of light are traveling straight. They hit a concave lens. Concave meaning it's thinner in the center, so it's like a cave. It's like the inside of a spoon, and it's spreading the light out. There's very few uses for these in real life. And also in the description, I will have a video that Shiloh and I made this afternoon using light rays and concave and convex lenses. So let's go to convex lenses. So with a convex lens, it's thicker in the center. So here's a convex lens. It's thicker in the center, and it's thinner at the end. I spelled meat wrong. That's funny. Okay, I'm sorry about that. It's thicker at the center. It causes light rays to meet at a focal point. What was I thinking? They use lots of optical equipment, including cameras, telescopes, microscopes, even things like magnifying glasses. Look at this kid right here. This is a good pastime for me, burning ants on the ground. So he's got a magnifying glass, and a magnifying glass, it's just a convex lens, and it focuses the light. If we look at our little ray diagram here, we can see that the light has a focal point. And beyond the focal point, the rays flip upside down. So here, this kid has figured out how to put the focal point on some ants, or maybe he's trying to burn some crayons. I don't know. But he's got the focal point right on the ground. And then if you were to pull it away beyond the focal point, whatever he would see through the magnifying glass would be upside down. Like I said, it's in cameras and things like that. It's also inside your eyes. So if you feel bored sometime, go to YouTube and YouTube cataract surgery or lens replacement, and the optometrist, ophthalmologist, I don't know, one of those people, they take the lens out of your eye, and it looks almost exactly like that. It's totally crazy. Again, there's a video that goes along with this. I want you to watch that video. It's very, very helpful. It's a recap on light. It will be in the descriptions down below. And I do believe that this is our last slide. So please watch those videos. Altogether, this lesson and those videos, we're talking like 25 minutes. And we're going to get a lot done in a short amount of time. I'm sorry we couldn't have class today, but please follow along. And if you're taking notes, please continue to take notes. And I will see you on Tuesday of next week. So have a great weekend. I need to figure out how to pause this.